All right, so let me now shift to an example. We will go ahead and see our very first example of how do we calculate the scattering matrix of a network. We're going to start with a very simple network. This is an electrically small T-junction. Essentially what that means is that you're coming from port number 1, and then you're splitting your signal to two different ports, ports 2 and 3. And to make life simple, to make things simple as we're getting started here, we will assume that the characteristic impedance of all ports are the same. So Z0 is the characteristic impedance of ports 1, 2, and 3. And we will also assume that this is an electrically small junction, which basically means that this length is practically 0. And that's true for all ports. So a very, very small junction that you will see actually in real life. So what we want to find out here is the entire S matrix of this device. So let's start with calculating the S11 as our first example. So S11 means that I am looking into port number 1, and as we discussed before, this will be equal to B1 divided by A1, provided that A2 and A3 are basically 0. This is the defining equation for S11. And so since this is what I have to do, I will go ahead and ensure, first of all, that my A waves in ports 2 and 3 are equal to 0. So as I mentioned before, I will go ahead and terminate them with their own characteristic impedance, which in this case is equal to Z0. That again will ensure that both A2 and A3 are equal to 0. Then I will excite port 1 with some wave A1, and then I will try to calculate what is B1, and then divide B1 by A1 to find out what is S11. So essentially what we're looking at here is a reflection coefficient. We're looking at the reflected power in port 1 when there is some power launched into port 1, and that's the power wave A1. So all I have to do here is look at the characteristic impedance of my port 1, which will be equal to Z0. Look at the impedance that is terminating this transmission line. This impedance is very simple to find, is actually Zin, and is the parallel combination of the impedances you see from port 2 and port 3. And since those ports are electrically small, the impedance you see here is actually Z0, and the impedance you see here is also Z0. So you have two impedances Z0 connected in parallel, so that means that Z input, that's the load impedance as far as port 1 is concerned, is going to be equal to Z0 divided by 2. So equivalently, we basically have port 1 terminated with an impedance of Z0 by 2. The characteristic impedance of port 1 is Z0. So that means if I go ahead now and calculate S11, which will be equal to B1 by A1, this will be nothing else as Z input minus Z0 over Z input plus Z0. So in other words, this is the reflection coefficient that you see into port 1, provided that ports 2 and 3 have been terminated with their own characteristic impedances. And of course, it doesn't take much to find out that this is equal to negative 1 by 3. So this is the classic way that you will be calculating the S11 of any network. You will go ahead and terminate all the other ports with their own characteristic impedances, and then find the reflection coefficient into port 1. The calculation here was very simple because the electrical length of this network is very, very small. But really, even if there was some type of electrical length into these ports, then you would simply have applied the equation we have learned to find out the input impedance of a line. For example, here we would have done that the Z input into port 2 would have been equal to Z0, and then we would have ZL, which is also Z0, plus J Z0 tangent beta L, while L may have been the length of this, over, and again, J Z0 over J Z0 tangent beta L. So my point is that we used here the short transmission line length to make the calculation simple, but even if this is not a simple, even if it's not a short transmission line, the result can be found in exactly the same way. Now, this is a perfectly symmetrical structure, so now that I do have S11, I can basically make the argument that S22 and S33 must be the same. It is really the same thing, just looking at it from different ports. In addition, this is a reciprocal structure. There is basically just a bunch of transmission lines here. So that means that SNM will be equal to SMN. So in other words, it doesn't matter if you excite port number 1 and you look at, let's say, B2 or B3, you can also excite port number 3 and look at the output from port number 1. That's what basically reciprocity says. So that essentially means, for example, that S12 will be equal to S21. And this is a general property, as we'll see later on, for all networks. But I would like to use this property for this network to essentially make life simple. So basically, because of symmetry and reciprocity, I don't really have to calculate much more here. What I do need to calculate is essentially my S21. So now let's see how we're going to calculate S21. And let me go back and show you this figure again. So S21, as we discussed before, is essentially going to be equal to B2 divided by A1, provided that A2 and A3 are equal to 0. So I have to take my network and set it up such that A2 and A3 are equal to 0, and then calculate B2 and divide that by A1. All right, so how do I do that? So again, I need to take my network, terminate it with its own characteristic impedance for each port, so Z0 for 2 and 3, and then look at what is the power wave B2 that will end up into port number 2 under these conditions. All right, so this is something that is relatively easy to do, but first of all, let me simplify the circuit. So the circuit now has, again, Z0 on each of the ports. That means that Z input here will be equal to Z0 by 2, as we just did before. So let me also say that I will have some voltage into port number 2. So this is voltage V2, this is voltage V3, and this is voltage V1. So the key to calculating S21 in the networks that we will see in this class is to find a way to relate the voltages V2 and V1, or V3 and V1 if you were calculating S31. Once you can find that relationship, then calculating S21 will become immediate. And so let's see how we will do that. So first, let me simplify the network by redrawing it and giving you the network now as it looks from port number 1. And of course, as I mentioned before, the input will be equal to Z0 by 2. I've drawn that here. And since I'm also looking at an electrically short network, the voltage right here is the same as I would have in V2 and V3. Those were in parallel. So V2 is going to be equal to the voltage. It's going to be equal to the voltage across the Z0 by 2 load. And of course, V1 is the voltage at the input of the port. Given that this is electrically short, V1 obviously equals V2 and V3, which is, as I said before, the key to finding the S21. So let's go through the calculation so you can see it. We will start by looking at the voltage equations and how those are related to the power waves. We basically found at the beginning of the class that this is the voltage at the network in port 2 will be equal to the square root of the characteristic impedance at port 2, that's the Z0 in this case, times A2 plus B2. So again, this is the equation that we saw in the beginning that explicitly relates the power waves to the voltage. Since we have connected now the characteristic impedances Z0 at ports 2 and 3, that means that we have guaranteed no reflections from those ports, so A2 should be 0. And so that means that V2 is going to be equal to square root of Z0 times B2. And that is true for all cases when you make sure that A2 is equal to 0. There is actually no assumption behind this equation that is true only for this network. It's actually true for all networks as long as you make sure that A2 is equal to 0. In other words, as long as you make sure that the port is terminated to its own characteristic impedance. Similarly, let's look at what happens in port 1. In port 1, the voltage V1 will be equal to the square root of its own characteristic impedance, Z0 in this case, times, of course, again, A1 plus B1. Now, since V1 is the square root of Z0 A1 plus B1, and I already know that B1 is equal to S11 A1, provided, of course, that A2 and A3 is equal to 0, which they are in our case, then I can simplify that expression and write it as square root of Z0 1 plus S11 times A1. So again, there is actually no assumption behind this equation that is true only for this particular network. This equation I wrote there will be true for all networks as long as you make sure that all the ANs, except for A1, are going to be equal to 0. So now if I divide these two equations, I will basically be able to get the very simple that S21 will be equal to B2 divided by A1 times V2 by V1. Now that's where I need this equation. Because V1 is equal to V2, and that is something that happens only for this network, I can basically write that the S21 will be equal to 1 plus S11. And since I have found out that this is equal to negative 1 by 3, the S11, this will be actually 2/3. So let me go through this calculation once again to make sure that we don't have a misunderstanding. So the first two equations I wrote for V2 and V1 are true always for all networks, no matter what, provided that you have terminated the network with its own characteristic impedance. So you can apply this all the time, and so you will always end up dividing these two equations, and you will always end up having to find out the relation between V1 and V2. So you can use any of your circuit techniques to do that. In this case, it's very simple. V1 is equal to V2, and that's why this will yield the S21 to be equal to 1 plus S11. So based on this, I have basically now written my entire matrix. The S21 I just calculated is right here. So this is the 2/3 that you will see, of course, with a multiplication factor right here. And the same thing will be equal to the S31. Obviously, the network is symmetric, so S31 will be equal to 2/3. And because of reciprocity, S12 will be equal to 2/3, and S13 will be equal to 2/3. Negative 1/3 will be S11, S22, and S33. That's the main diagonal of this matrix. And now we have basically solved all the S parameters for the three-way splitter.